Hello. Today we will be talking about a security alarm. But before that, I'd like to say a few words about myself. I am indeed lead researcher at Possible Security. We do penetration testing, consulting, and training, stuff like that. And I am quite active on Twitter. That's the only social network I use, because it doesn't try to fool you into some privacy that's not there. But both by day and by night, I focus on different things. One of that is network flow analysis, which is what allowed me to research how this protocol works, which allowed me to look into it. Also reverse engineering, right? This is what it's all about. And part of the presentation is going to be about giving you the tools and giving you the skills, the audience here today and online, to be able to repeat these things for this system or for a different system, if you so wish. I also do social engineering, so some people say you should be careful, but maybe I'm not that good, in that. And I have been doing IT security for quite many years, so I got bored with the technical stuff, so I also do legal dimension from time to time, like policy documents, ISO standards, and stuff like that. Anyway, let's talk about security alarms. Many of you have a security alarm system in your home, or maybe in your office. The goal of a security alarm is, of course, to protect you in case of a break-in. And some security alarms have gotten really good at achieving this goal. So some of them are literally preventing attacks, like this one demonstrated here. It's a smoke screen alarm system, and when the alarm goes off, it just prevents the attacker to be able to see and to be able to do whatever they're there to do. But it's still a security alarm, and it still has its vulnerabilities. So the question we're asking today is, what could go wrong with an alarm system? Let me ask you something. When did you last change the code for your alarm system at home, or when was the code last changed for your alarm system at work? For who of you it has been in the last 3 months? Can I have a show of hands? Last 3 months? Last 12 months? A year? Never? Anyone never? Okay. So these codes, we usually don't change them, right? Even though we can, we don't change them when they're installed. So one thing that could go wrong, what if an adversary could fool the system with a small device and slowly brute force your 4-digit code? Of course, there are lockouts. If an attacker were to come on your premises and try to punch in the code, it would block the system after a couple attempts, usually 5 attempts. But if an attacker were to install an automated device, they could brute force the system slowly, say 4 codes per hour. With 4 codes per hour, we get 96 tries per day. You know what that gives us? We can test all 4-digit pins in 3.5 months. And since you don't change them, well, attacker can simply brute force your code. There are some other things that can go wrong. So the goal of an alarm system is to provide you the peace of mind. The question is, do we get the peace of mind, or do we have something to worry about in addition to what we would have otherwise? So let's look at one typical scenario. This is a warehouse. It stores your stuff. Maybe you're a company selling hardware. Your stock is in there. Maybe you're selling food. Maybe just you have expensive equipment that's used to make different merchandise in there, right? And it's a large warehouse, so you would usually, on such a system, you would have like a keypad or 2. You would have some sensors, like passive infrared sensors that detect movement, or magnetic sensors that detect when a door or window is open. But in reality, what happens with these large deployments is that there's a main entrance right, on the left here, for example. And some of the keypads get rarely used. So they're there, they're working, but no one uses it for a week, maybe for a month. No one goes there and checks on the condition of the keypad. And sometimes keypads are being installed outside, so you can disarm the system before entering the premises, right? So what if attacker was able to use that remote keypad of your device to extract some information about your security zoning or about your security configuration? Or maybe attacker could use that keypad that you aren't using to extract the code you use to disarm the system directly without guessing. So that's an attack we're going to look at today. So once again, the goal of the rest of the presentations here is to acquaint you with the system that I tested and to let you repeat the research yourself, to be able to look into protocols you don't know, to be able to test the security of some closed systems that you don't have the source code for. And of course, we're going to have a live demo, as you can probably tell from this huge box over here. That's going to be at the very end. So let's talk about what I tested there. So some time ago, I looked into this security system here. It's made by Paradox Security Systems. It's a Canadian company with some history. It's quite popular in some parts of the world, not only Canada, and it's considered the cheaper alternative by some to like DSC or some other larger vendors. And what they make is basically modular security alarms. That means it's an alarm that you can expand, or rather that the company that installs the alarm for you can expand. They have 3 different versions. The Spectra SP, it's just expandable security systems. It's the entry version. It's the cheapest one, right? Then we have Evo, which is high security and access systems. It's meant for places where you need higher security. And then the third one they added, the last, is Magellan. That's wireless security systems. If you don't want to ruin the walls on your new house, you can just have a wireless system and it communicates wirelessly. And the question to ask here is the protocol secure? Because for the wireless system, it's even more important, because there's nothing preventing the attacker from capturing the data. It's simply about decryption. I want to acknowledge some prior research that's been done on Paradox Security Systems as well. So there's been some work on interfacing with SP series, so Spectra series, the low security series via COMBUS. It's been done by Martin Kharzanov. And he did publish a partially working code, a small bit of code, but moved on to doing serial research. And there's been some work on working with Magellan systems via serial. It's all over forums, but there's this one person from Lithuania, which is a country nearby Latvia, Gytis Ramanauskas, who actually posted some code on GitHub. But once again, this code has to deal with serial, and I'm going to show you in a minute why it's not applicable to possible security attacks. It's good to interface with your system, but security is not really directly affected from that. Of course, when I found the problems I'm talking about today, I contacted the company, Paradox Security Systems. What I got at first was, we don't think you actually have anything. So I just sent an email saying, hey, I found a problem in your systems. They answered, well, we're not sure. And they asked for more data. So as a security researcher, I, of course, went ahead and tried to establish a secure contact with their security team instead of just sending it to support. I was met with what was clearly no process. There was no responsible disclosure, no vulnerability handling process there. I ended up talking with the support. They promised to forward some of my emails to security. And the last technical email I sent to them was, there's this problem on the COMBUS. You can intercept the codes. That was as technical as I got. And they said, thanks. the information has been dealt with, even though I never got to send them my proof of concept or describe what it is exactly. So I inquired further, and what I got was this magnificent email. Yeah? For obvious security reasons, it is our policy to never discuss engineering matters outside of the company, and thus we will not be commenting further on this issue. So I gave them some time, and a couple of years later, I'm here doing public disclosure on the thing. So let's take a look at how the system is set up. Each of their security systems is modular, but it does consist of the master. That is, the master panel is the heart of the system. You can call it the motherboard. This is a cheaper version from Spectra. This is SP65. In fact, the cheapest one you can get. I think it's around 40 euros, maybe 50 euros to get this one. Then we have some ancillaries, right? You need the battery. In case the bad guys cut your power supply, you still need the system to work, of course. You have the power supply as well, like a transformer. You have a siren, like a loudspeaker that alerts your neighbors when an intrusion is happening, of course. And there are COMBUS slaves, and this presentation is actually focusing on COMBUS specifically. So we are going to look at the COMBUS protocol. And these are some of the examples of COMBUS devices. The feature of COMBUS, this common bus, it's a proprietary bus made by them, is that it provides two-way communication. So the slave device can communicate with the panel, with the master device, both ways. Notable example of COMBUS slave is a keypad. Every keypad is a COMBUS slave. But there are also some other examples, like here you can see this green one, it's a printer module. So you can, as you can see, you can connect the good old parallel port to connect to the printer. You can use a serial port, and you can use even the USB. So in case you want to connect a printer to your alarm system, you're covered. So you can use COMBUS to connect to your printer. Or there are some other devices like Listen-In, where you can call a system and spy on what's happening in your apartment or in your office via microphone. Of course, every alarm system has to have sensors. And those are zone interrupt devices in Paradox, which means it's just an input device, two wires, ground and zone wire, and it measures resistance, which allows for chaining. You can connect multiple of them on one line. And some of the examples are magnetic sensors, passive infrared sensors, panic buttons, that simple stuff. And it's one way. You only get input from the device. You cannot communicate back. And PGM modules is the other way around. This is output. This allows you to configure your alarm system on specific conditions, on specific criteria, like, say, movement in area 1 but not area 2, or zone 1 and not zone 2, to switch on a PGM output. And it can drive a device up to 100 milliamps with a relay. You can, of course, drive like a light bulb or something more powerful. So that's another thing that we have there. And of course, there are serial devices, which is what most of the research has been on so far. It's a RS485 protocol, and some examples include serial converters that convert it to USB or classic serial RS232, IP modules, GSM modules. So imagine that this device, which is, as we will see today, not very secure. It even has IP connectivity these days, and it's on the internet out there, with protocols that are written, I would imagine, in quality similar to what we'll see today. And today we're looking at Evo 192, which is the expensive one. This is the secure one, the high security system. This is what we have here today. And I'd like to point out some of the things on the panel, right? Remember, I'm going through step by step, so everyone can follow and everyone can repeat the research if they intend to. So if you look at the panel, we of course have some power connectors, right? We have, according to the instruction manual, we have 16.5 volts AC, alternating current, input there through the transformer. We have the battery connector for 12 volt acid battery. And we have the real-time clock battery for 3 volts, which is used when your main battery fails and alarm system doesn't work at all. At least your clock stays moving forward. We have the COMBUS, which is what we're talking about here today. So the COMBUS consists of 4 wires here. And nicely for the installer, there's also another COMBUS connector called serial keypad where you can connect directly on the panel. But for an attacker, the panel is usually hidden far away from the door. It's usually hidden in the furthest corner of the building where you cannot access it, and it's correct to do so. So we're more interested in the COMBUS that actually goes to the keypads and other intelligent devices. And of course, I can't skip, and I have to mention the other protocols that are there on the panel. The serial protocol, RS485, of course. Voice dialer, which is used for dialing a modem via voice, calling the police automatically and saying, there's a break-in, come to this address. And memkey. This is quite a cool one, and if someone would like to research it, I'd be glad. So memkey is this interesting protocol where they have this USB stick that you can plug into a computer, and on the second side of the stick, you have a connector that goes into memkey. If you plug it into the panel, it can either copy all the configuration from the panel or write the configuration from the USB key to the panel. So it's quite a cool one. I would imagine there might be some security vulnerabilities there as well. So how do we proceed with reverse engineering this panel, this high security panel? These are the hardware tools that you'll need. Digital signal oscilloscope can also help a lot. I started with that, but turned out I didn't need to. So you have a logic analyzer, you have let's say Arduino Uno that you can use to talk to the device, right? You have these ports here that you can use to connect to the device. Now, let's take a closer look at COMBUS. So, as we know, COMBUS consists of 4 wires. And if we take a look at an installation, we will see that the wires use the colors red, black, green, and yellow. It's a 4-wire bus. One thing particular about COMBUS is that all the slaves and the master are electrically connected on each of the wires. So it's a direct connection. There's no magic. There's no switches, no routers, nothing like that. It's an electric level connection between all of them. In practice, it of course means that what one slave sees, all the other slaves see as well, because there are no active components on the wire, even no diodes there. So all the slaves communicate in the same space. Now, if you look at the right side of the slide, these are some layers that I deduced might be under COMBUS. So this is not official documentation. This is just what looking at COMBUS protocol, how I structured it so it's easier for me to talk about it. So there's electrical layer at the bottom. Electrical layer talks about voltage levels, about which wire is which, right? Then we have the signal layer over there. And signal layer talks about frequency, the clock cycle, the bit width, the delay between packets. So that level stuff, signal level stuff. Then we have packet layer, and packet layer talks about packet format, how the checksums are made. The command layer describes different commands that exist on the COMBUS. And finally, the payload layer talks about encoding some of the data. So I did a full analysis on COMBUS, and this is what I came up with. Let's take a look at it layer by layer. So once again, how can you reverse engineer it yourself? Right? If you buy a demo kit like that for, I don't know, like a couple €100, and you look at the keypad, this is what you get, right? If you turn the keypad around, on the other side you will see these connectors and you will see some wires going in. This white large wire here is the COMBUS. It goes to your panel. You may also have a zone connector here, right? If you have, let's say the keypad is near a door, the zone connector might go to the sensor on the door, and then it would be sent through the COMBUS to the panel itself. But we're interested in the COMBUS here, which is yellow, green, black, and red. So, not knowing anything about the system, what is something that we can do? We can take a multimeter, and we can start sticking it in different places on the keypad, of course. So we already identified that these 4 wires are the COMBUS, and black and red, as we know from electrical engineering is usually used for powering, right? So let's try those. Let's measure voltage. At first, let's measure resistance between black and the ground. Let's see if it really is a ground, right? And measuring resistance, we get 0. That means black is our ground, right? Then we can measure the voltage between black and red. We measure the voltage. We get a stable DC, direct current, on there. That means red is power, right? So we have clearly identified the black and the red wire. There are just 2 wires remaining, the yellow and the green, right? So we can plug our multimeter in there, and we don't get any normal voltage reading. We get it fluctuating a bit. So those might be data wires, but we have to go deeper. We have to go further. So to do that, we have to look at the signal layer. And if we use a device like SALA logic analyzer that I showed you previously, this is what we get. So I connect one probe to the green wire, one probe to the yellow wire, as indicated here. And this is the signal I get. And from here, looking at the time scale, I already get a lot of information out of here. So what I can see is that yellow is clock, right? If I take a look at it, yellow is either down or is going 1 0 1 0 1 0. So it's clearly clock. There is no data in there. And the green, then of course, remains to be data, because we see some changes. We see irregularities, different patterns on there. We can also read from here there are 40 milliseconds between packet bursts, right? So one packet ends here at approximately 70 milliseconds, and the second packet starts here at approximately 110 milliseconds. And we can also see that one clock cycle is 1 millisecond, right? If you look at the clock here, up, down, and back to the beginning, it's 1 millisecond. That means the signal is 1 kilohertz. Easily readable with an Arduino. It's not a high frequency at all. So looking at the signal encoding, we zoom in a bit. This is one single short packet. Right? We just zoomed in here. And if we take a look at it, we can see that when the clock is high, the data is also always high. That means it's all ones, so it's nothing there. Right? We can conclude that only when the clock is low, there are some differences on the data line. For example, here we have low clock and low data, low clock and high data. But if you look at high clocks, the green ones here, it's always also high on the data line. So our initial conclusion is that when the clock is low, we see data on the green line. And indeed, if we take a look at the bits, this is what we get. We get a packet 0C91 to D2T1, which, as we will see later, is a legitimate packet for COMBUS. But we have to keep something in mind. COMBUS is a two-way protocol. Keypad communicates with the panel, and panel communicates back to the keypad. So clearly, we are missing something here. So the question is what? And doing some more research, a couple tens of minutes, maybe a couple hours into it, we can conclude that the clock actually indicates which side of the communications is talking. What we identified here previously was the master talking. When the clock, the yellow one, is high, master is sending data. When the clock is low, slave is sending data. So it's a two-way communication channel where each bit goes from different side, right? So how do we set up the hardware to read the data? So this is a COMBUS wire coming in here. We are not using the voltage wire, of course. The voltage on there, by the way, is 12 volts, so you shouldn't stick it directly into Arduino. And the voltage, the maximum voltage on the signal wires is higher than Arduino tolerates as well. This is why we add resistors. This setup here is great for reading. It will not work for writing because of the setup, but you can use pull-down resistors to be able to write to the COMBUS as well if you wish so. So resistors here are to limit the voltage going into the Arduino and the current draw. How do we decode it into bytes? It's actually super easy. This is all it takes. This is pseudocode, but the code running on the Arduino is that simple. So we wait for a clock change. When clock change happens, we wait 50 microseconds just to be sure that we are not missing the first byte, right? Some desynchronization may be happening there. And then we see, if clock is high, master may be talking. If clock is low, slave may be talking, right? And since we found out that slave is pulling down to send 1, but master is pulling up, we need to invert the slave data, of course. Right, so that's what we do here. We invert the slave data over here, and we add it to the bits that we're collecting. And when we see more than 2 milliseconds idle signal on the clock, remember the clock cycle was 1 millisecond, so more than 2 milliseconds, we are sure that nothing is being sent. Then we look if we have gathered any data, and we print it out over serial. So that's as easy as it goes. That's how we take a look at the actual signal level on the COMBUS. Now let's take a look at the packet level. When we are done with signal level, what we're left with is these packets. For example, here's one. This is an event packet. It starts with E. That's a hex code E something. That's an event. And what we see here is the command. The first bit, yellow one, the first byte, sorry, is the command, the yellow one. At the very end, we see the green one. That's a checksum. So there is some checksum built in to prevent errors happening on the wire. And then there are 8 bits that are unused, just zeros in the end. Here's a different command. This is 0C. This is clock command. It's clock synchronization command. It's shorter. It doesn't have a checksum. But the long ones usually do. Looking at the slave, it's a bit different. Slave starts, as you saw from previous slides, if you were paying attention, with an unused byte. That is because some low-powered slaves may take some time to notice that the clock has started being sent. And that's where it's possible that this byte that the slave may not be able to send the byte as fast. That is why I believe the protocol mandates that the first byte by the slave is always unset, unused. Then it's followed by the channel request. Second byte is set to 2, which means that slave wants to talk. And in this case, it's it. Command 0 means there's no command. This is what happens when a slave wants to talk, right? Because we have multiple slaves, multiple keypads, multiple devices on the COMBUS. And if multiple of them want to talk at the same time, this is what they use to indicate that they want to talk. Here is a different command. This is a command where an code is being entered on one of the keypads. Again, it starts with channel request, it starts with a command, and there's a checksum at the end. And then we have an unused byte there as well. Checksum is calculated super easy. So it's basically a summary checksum over 100 in hex, so over 256 over 1 byte. It rolls over, and you start to calculate it from the command, meaning that in this case, in the last line here, you don't take the 0-2 into account when you calculate the checksum, right? So that's how you do the checksum. Let's look at some specific commands, because I also decoded some of the commands, and one of the commands that we're going to see in the demo is the heartbeat command, or the clock command. An example of the command is seen right here behind me, 0C AA 1011. So what does it really mean? This is how it works. So 0C is a heartbeat or clock command, and next byte is a sequence number. And sequence number, it goes +1 all the time, and then it rotates back to 0, right? From 0 to 255. But what's also important is the last bit, or whether the sequence number is even or odd. If the sequence number is even, then the data being sent is the day of the month and the hour, like in this example here, right? It says it's 16th of the month and hour is 17th. And if the bit is odd, then minutes and seconds are being sent, right? In that case, those two last bytes would mean minutes and seconds. For the code entry, it's more interesting, because this is where the holy grail is, right? Remember, if you have this keypad as the other side of the warehouse that's not being used, we can connect a small, or maybe not so small device even, to the keypad, to the COMBUS, and we can leave it there and wait for someone to come and use the system. And then we can see the data being sent. Now, this command here decodes to that. This, of course, is sent by the slave, as indicated by 0002 at the beginning here. We have the user type here. And if the first bit of the user type is 1, it's a programmer. So programmer is a user, it's like installer. It's an employee of the company that installed your security alarm. They have higher access levels. They can reprogram the whole system. If it's not 1, it's a normal user. CT is the code type, right? What kind of code is being typed in? And as you may have guessed, CC is the code itself. So in this example, you can see that the code being typed on the keypad is 1, 2, 3, 4, which is quite an easy case, because they do have small amount of obfuscation in there. And then there is a serial number of the source device as well, because all the devices on the COMBUS are being enumerated when the system boots up at first. And I would wager that they have some kind of authentication on their source authentication, so seeing if the code is coming from real device. But the thing is, it seems to me easier to spoof than even Ethernet, because it's just 4-byte serial number, which actually matches what you have on the back of your keypad or the back of your device. And of course, there's a checksum computed using the rules already described. Now let's look at the payloads. Right, this is the final level of COMBUS. As we saw from these examples, and as I can confirm from other commands, there is no encryption used on the COMBUS for the payloads. Text is sent as fixed length string, ASCII string, and it's often 16 characters. It's the most common length of the text. And it uses space character as a filler to send a shorter string. Numbers are usually packed binary code decimal. As you saw, for example, the code on the previous slide, it was 1, 2, 3, 4, even though the decimal values for those hex values are different. But it's BCD, binary code decimal. But there is one thing they tried to do. They tried to use some obfuscation. So in case your pin code or any other constant has 0, we replace it with A. So it's not that easy. So they don't have an encryption, but at least we have some level of obfuscation. So now with that being said, I'm going to show you some demo. And the official manual says that before connecting a module to the COMBUS, you have to remove the AC power and the battery power from the control panel. Well, we don't have time for that, so we're not going to be doing that. We're just going to connect it to a live system here. So I have a keypad here. Let me show it to you. I have a keypad right here. It has a COMBUS wire going in. And what an attacker can do, attacker can cut into the COMBUS wire at any point and access the wires in here, right? You can strip the isolation from the small wires here. And then we can use our device to actually read what's on the COMBUS. So now I'm going to switch back to the laptop just for 30 seconds and show you the other part of the demo here. So I'm going to launch a serial terminal that will read what's happening on the device. Currently, it may be some random data, maybe some garbage, because the wires are just loose. They're not even grounded. So we're lucky to have zeros. I'm going to switch back to the camera here, and I'm going to now connect the wires that go into Arduino through the resistors to the COMBUS here. I'm going to start with ground. So I'm going to make sure that my signals are grounded. And this is how an attacker could do it as well, of course. So then I'm gonna connect the clock. Right, that is a yellow, of course. Okay. And then I'm going to connect finally the data, which is the green one, right? We make a small cut in the isolation of the cable, and we pinch into the green one. And we make sure that everything is secure on there, including the clock, of course. So this is how an attacker could connect to the COMBUS. Thank you. Now, if we take a look at the data being sent, we can already see some data being processed. And that is that small script that I showed you on the screen. It's basically 6 useful lines of pseudocode. And it's already processing. We see 0C, which is what? That was the clock or the heartbeat command. And we have zeros being sent back on the other bytes, on the other bits from the keypad. Now, this is unreadable for most of you, I guess, right, who don't read hex at a huge speed. So what I'm going to do now is I'm going to use a Python script to interpret this data here. So I'm going to launch a Python script. It connects to the same serial. And we can see one packet sends the date and an hour, and the other packet sends the minute and the second. Right? So we can see it quite nicely here. Sometimes it doesn't send the date, but usually it's interleaved, one by one. Right? So in order to see something useful, we of course can't have this on the screen because we are getting this multiple times per second. So now I'm going to modify my script to mute the timestamp or heartbeat packets. I'm going to relaunch it. And now, let me clear the screen so it's nicer. And now it's muting the heartbeats, right? But what I see all the other packets. Let's say you open the door for your office, and what happens is it's being immediately sent over COMBUS. And all the panels now know that zone number 1 in area number 1 has been opened. We also have some indication, right? Letter T means there are troubles. In this case, the trouble for the system is that I don't have an RTC battery, so the clock may be off. Then we go in, we close the door behind us, and we see that the zone 1 is closed. And we see indication Z, which means that all zones are secure at that moment, right? We can also trigger some passive infrared sensors, right? For example, this one here, zone 3, opened, closed, and so on, right? So we can already read that, which is where most of the current research online ends at. They just want to interface with their systems, but not me. I want to make sure the system is secure. And to make sure the system is secure, I need to try and hack it. So let's say someone now comes to the keypad at the far end of your warehouse, where the attacker has installed the connection. They open up the keypad and then type in a code, right? As soon as the code is typed, it's sent over COMBUS, and the system decodes it, and the serial number is shown as well. I have removed some bytes from the serial just to protect the specific device number I have. And attacker can also see that this code was incorrect. It was not a correct code, right? Okay, but that's the device at the far end of the warehouse. It's not being used. The attacker has connected over there. But let's imagine that now you come to work and you use the keypad that you usually use every day. And you got your keypad and you type in your PIN code, your code in here, on a different keypad, right? The active keypad. It's still being sent over the COMBUS to all the devices on the COMBUS, right? And we can see the code typed in here, 0178 in this case, from a different device, and it's accepted. So the code is correct. And by the way, we can also see that it was a duress code, right? So we can even get that. Finally, even if you use something that's not connected to COMBUS, like for example, many of these devices, including this one, now come with a remote. You don't have to remember code. You can simply press a button and things will happen. It's wireless. It goes directly to this EVO panel. It's not speaking COMBUS, but still, because every panel needs to know the status of the system, this data is being sent over COMBUS. I press the lock button here, I get a red light, and we can see that the remote button lock was pressed. This is configured for user 1, right? Or we can as well unlock it, of course, right here, right? And even there are some more buttons, right? We can press the button on the right, or we can press the information button. So it's all being sent over COMBUS, and it's all being transcribed using the code that I wrote. So that's the demo. Let us get back to the slides. On their webpage right now, this is what the company says about this panel, EVO 192. Digiplex and Digiplex EVO systems provide the highest level of protection for banks, high security military and government sites, luxurious residential homes, and any place where maximum security is essential. So, well, that's the best they have, apparently. In summary, so the impact of the research that we did here. I built some hardware, and the decoding software I wrote as well. That means it's now available publicly. The company has had enough time to look at the problems, to fix them if they wish to. And I hope that other people will use it for good and will be able to test their own systems. I have partially transcribed the COMBUS protocol on the command level. So the lower layers are done. The command layer, it's partially transcribed. I think I've covered maybe 60 to 80% of it, so you can get a lot of information. Still, some of the commands will come up as unknown, so there's still some work to be done. And the possible attacks that I talked about at the beginning of the presentation, they can affect anyone, especially when you have installed a system thinking it's a high security system, but in fact it's vulnerable to some pretty basic 90s era security flaws, or rather lack of security. So, of course, my research, even though I tend to try and find vulnerabilities in systems, I always want to provide a solution to fix the problem if they want to. So, solutions I'm going to provide here are, some of you may say they are a bit over the top, a bit too much. And it's true. It can be done simpler if needed. However, if done in a simple manner, there's risk of implementing bad self-made cryptography. So since the systems are powerful enough these days, all the modules are powerful or can be powerful enough with low power consumption, huge processing power, and small enough form factor, I think we need encryption and command layer, of course. And with powerful devices, a good protocol that's been vetted and tested is the same we use for banking online. We can use TLS, right? Once again, it may be a bit too much, but implementing your own homemade security protocols, cryptography protocols, sometimes ends well, mostly doesn't. How do we implement TLS in a system that's not connected to the internet? All components should ship from the factory with certificate authority in their trust store, of course. As an added benefit, if Paradox Security is listening to this, the this also would allow them to sell licenses, right? CA works for 10 years or 20 years and then expires. So that's also there. We also need mutual slave-master authentication. It's not about encryption. It's not only about protecting the data. It's also about making sure that unauthorized COMBUS slaves do not send in any data. Client certificates can be used for that. Easy part of TLS, right? And that can be used. Each panel can ship with a client certificate. Now, in addition to that, in addition to TLS, I believe in security in depth. So I think that sensitive payloads like codes should also be encrypted in addition to TLS. And it could be easily done with unique per panel key. Almost no one in this room installs the security systems themselves. We trust professionals to do it. And when professional comes to install it, if the manufacturer would provide this, it would be possible for them to synchronize a unique key to all the devices connected to a single master, to a single panel. And that way we can have sensitive payload encryption as well. Now, a bit about further research. And I know some of you here love to hack signals or love to hack other stuff. So if you'd like to contribute, it's going to be, it is on GitHub, and I'm going to show you the link. So please contribute. Please help me with advanced security research here and understand how really secure are we when we're using security alarm systems. So one thing that I need to test still is denial of service attacks. Is there a possibility for the attacker to come in and simply disable the system? Right? Because why do we have the battery for the system? We have it so that the attacker cannot simply cut the power line to your house and break in. That's why the battery is there. But is there some other type of attack that we can use to disable the system immediately? Emulating a slave is an interesting avenue of research. So actually setting up pull-down resistors on the Arduino side and trying to emulate a slave, trying to send in data, trying to guess the pin code, for example, over a period of 3.5 months. COMBUS over radio, very interesting topic. Remember these Magellan systems? Those were wireless. So if those are wireless, do they still talk COMBUS? Is it still not encrypted? If so, it means the attacker doesn't even have to connect to your wires. They just have to point an antenna in the general direction of your house or office to listen to what's happening on COMBUS. These are open questions. I don't know. But if it's the same COMBUS without encryption or with weak encryption, then we got a problem. Radio frequency attacks. Those are quite interesting as well. And I've started looking into that a month ago. So this is a different protocol. It's not COMBUS. It's being sent over 433 megahertz. And the question is it secure enough? Or is it just a rolling code that's been defeated on cars some time ago already? Finally, another fun part that I'd really like to do, but it does take a lot of time and is a completely different avenue of research, is reverse engineering the firmware, right? Instead of looking at the live system, just looking at how the firmware is set up, trying to dump the contents of the memory of the panel, trying to see if I can get to the assembly behind it, trying to see how the codes are stored on the panel itself. Can a visitor to your office access the system and dump your codes unnoticed, for example? So that is the further research that I'd like to look at. The slides will be on Kirils.org, of course also on official site for the conference. And the source code is available on github.com, 0KI paradox. So you can take a look at that. You can play around if you have a system like that. Of course, do it legally. And please do contribute if you find anything interesting. Thank you very much.
Thank you so much, Kirils. Do we have any questions from the crowd? Anyone? All right.
Thank you so much. Your presentation was very helpful. I have a question. As you have demonstrated, in order to conduct such type of attack, so that means the physical security is already breached, right? So that means you have a bigger problem. Attacker is already in your environment. So how do you see such type of an implantation by the hacker in any secured environment?
Especially in secure environments, delay is not used for alarm. So as soon as you open the door, our alarm goes off. It's configurable, but in highly secure environments, they usually configure it like that. So that means, in turn, that the keypad has to be outside of the secure zone for the alarm not to go off. And if the keypad is outside, an attacker can access it. And of course, it's just a prelude to further research, for example, for COMBUS over radio, where you can access it remotely. Any more questions, maybe?
All right, then. If that was it, then thank you so much, Kirils, for your talk.
Thanks. I'll be around.